In this lecture, we will discuss about the series RL and series RC circuits, and then we will have an introduction of the impedance. So this lecture covers the analysis of series RL circuit, series RC circuit, and the concept of impedance. First of all, we will discuss about series RL circuit. What is series RL circuit? So when you have a resistance of value R and an inductor of some inductance L connected to one another in series, so such type of circuit, such type of combination, when is connected to an AC source as shown here, so this circuit is known as series RL circuit. Now the purpose of this lecture is to understand the composite behavior of the two components when they are connected together. Because in previous lectures we discussed the behavior of the individual components, like a pure resistive circuit we have discussed, pure inductive circuit we have discussed, and similarly pure capacitive circuit also we have discussed. But as we know that our most of the circuits, more than 90% of the electrical systems or electrical circuits are composite circuits. Composite circuit means the circuits which are comprises of which contains all the electrical components including resistance, inductance, and capacitance, or resistance and inductance. So the behavior of such circuit, which is a series RL circuit as shown here in this diagram 1. So in this, if you see, this particular combination R and L is connected in series to a voltage source V. Now this capital V is basically the RMS value of the input voltage, which is given by V is equal to Vm sine omega t. Now, this voltage V delivers some current I. Now, this capital I is the RMS value of the current, means the instantaneous current I. So, this current will flow through the resistance R, and same current will flow through the inductor with inductance L. Now, when this current will flow through this inductor R, resistance R, it will have certain voltage drop across this resistance, which is given by VR. And when the same current will flow through the inductor of inductance L, a voltage drop across this inductor will be there, which is given by VL. Now VR is basically equal to I into R, where this is the RMS value of input current and VR is the RMS value of voltage across the resistance of value R. Similarly, this VL is given by I into XL, where I is the RMS value of current and XL is the inductive reactance. Now, these are the equations basically. Now, as far as the phasor diagram is concerned, so the phasor diagram of a resistance and and the inductor basically is also shown here. You can see that the voltage drop across the resistance R and the current through this resistance R are in phase with one another. That means the phase difference is zero here in this case, 0 degrees, because this is the inherent characteristic of the resistance, that the current through a resistance and voltage across a resistance will have zero phase difference. Or in other words, we can say that these two will be in same phase. Now let us come to the inductor, whose value is L. The voltage drop across inductor is VL. And as we all know that in an inductor, the current lags the voltage by 90 degree. Now when you draw the diagram, the phasor diagram of an inductor, it will be like this. So taking I as the reference phasor, so VL will be 90 degree leading the current. You can also write it in this word that voltage VL leads I by 90 degree in an inductor. So when you combine the two phasor diagrams, So the two phasor diagrams can be combined and are shown in this diagram number 2, the figure number 2. You can see, because here the current phasor is common. So let us draw the common phasor first of all, which I. Now the voltage across resistance, which is VR, is in phase with this I, and the voltage across the inductor, which is VL, is 90-degree leading the current. The resultant of these two phasors means VR and VL is equal to V, and the phase difference here is phi. So this phi is basically the phase difference between V and I in this particular circuit. So from here we have understood one thing, that in a series RL circuit, the voltage leads the current by 5 degrees and not by 90 degrees. That means we have a resultant value of the two phasors, VR and VL, which is equal to V. So you can see here this V is leading the current I by some angle phi. So this is the concept related to the series RL circuit. And most of the circuits, most of the electrical appliances are basically the RL circuitries. Let it be your fan, let it be your electric motor, or any other electrical appliance, is more or less is an RL circuit. Means the circuit which contains both the resistance as well as the inductance. So capital V and capital I are the RMS values of voltage and current in this case. And let us come to the next page. Now you can understand this with the help of the waveform also, because the current here in RL circuit is lagging the voltage, or you can say the voltage is leading the current by some angle which is phi. So this is phi difference. That means the current will start its journey 5 degrees after the voltage has started. So assume that the voltage has started from 0 degrees, means it is the reference phasor, and current will start after 5 radians from the voltage. So at every point of time, the current and voltage will have a phase difference of phi. Now we have two components of the voltage V. This capital V is actually the RMS value of input voltage. And now if you go through the diagram, the phasor diagram here, this axis is basically the imaginary axis, and this axis, x-axis, is the real axis. So that means the resultant V is the complex number. It is a complex quantity which is given by V is equal to VR plus JVL, and this is in terms of RMS. So we can take its magnitude. The magnitude is under root VR square plus VL square, and we can write VR is equal to IR and VL is equal to IXL. So we have V is equal to I under root R square plus XL square. Now from here we will have the value of current I, which is equal to V by R square plus XL square. Now in this particular equation, this particular quantity, if you compare it with the standard equation of the current, so current is given by, it is given by the applied voltage and the resistive force. Now this resistive force, if you compare this equation, this is the applied voltage and resistive force. So if we compare the apply this equation with this particular equation here, so we have current is equal to voltage by some factor which is under root R square plus XL square. Now if you compare this with here, so this means that the quantity under root R square plus XL square is nothing but the opposition offered by the circuit to the flow of current, and this is what we call as impedance of the circuit. So basically impedance is expressed in with Z. This is the capital letter Z, and it is measured in ohms. So now This is called as impedance. And the triangle which we discussed here, if you divide this triangle with I from all the side, so we have this V by I is equal to Z. This is equal to XL basically, because XL is the inductive reactance and VR by I is the real component, so it is equal to E. So now if we divide this phasor, every phasor in this triangle OBA with I, which is the common component here, because current is common in this particular circuit. So we have a new kind of triangle which we call as the impedance triangle. So impedance triangle here is XL, which is the virtual component, and R is the real component, and Z is the impedance, and phi is the phase difference between the voltage V and the current I. So that means your Z is basically a complex quantity which is given by the real plus imaginary part. And when you take its magnitude, so its magnitude will be, you can see here in this formula, its magnitude will be equal to under root R square plus XL square. Now the same thing is given here. So that means this particular quantity is known as the impedance. Under root R square plus XL square is nothing but the impedance, and it is generally measured in ohms, and it is denoted by a capital letter Z. Now let us come to the next slide, which is related to series RC circuit. Now series RC circuit is basically such circuit in which we have a resistance of value R and a capacitor of value C connected to one another in series. So when we have such combination with us and connected to an AC voltage source which is having an RMS value of V, so such circuit is known as series RC circuit. Now in this circuit we have a current which is because of this voltage V, and these two are the RMS values. I and V are the RMS values of voltage and current. Now if you see here, in this we have the same current is flowing through R as well as C, and then we have this one, right? Now, when this current I will flow through this R, it will have certain voltage drop across R, which is given by VR, and the same current when will flow through capacitor of value C will have a voltage drop of VC across this capacitor. Now, we know that as far as our resistance is concerned, the voltage, the phasor diagram or the phase difference between the voltage drop across R and the current through it will be zero. So this is how you can represent as far as our pure AC circuit is concerned. Now, if you see the capacitor, so in capacitor we know that the current leads the voltage by 90 degree, or you can say the voltage lags the current by 90 degree. So taking I as the common phasor here and here on both sides, we have a new triangle OAB here, in which we have VR is in phase with I, which across the capacitor, which is, it is the RMS value, and V is the resultant vector basically. So the same thing can be applied here also. If we can draw this with I, all these three phasors, so we will have a new triangle in which we have VR by I, the real component, which is nothing but R. Then we have VC by I, which is nothing by XC, and then we have a resultant, which is nothing by but Z. And phi is the phase difference. This is the phase difference between V and I. So this is what we call as impedance. So the purpose is to understand the composite behavior of a circuit in which we have a resistance and capacitance connected in series with one another across an AC source. So a series RC circuit is the one which is shown here, where V and I are the RMS values of the input voltage and current, and then we have rest of the things here. Now you can understand the same concept with the help of waveform also. Now because here the current is not, now if you see this diagram, this one, in this triangle you can see the current is leading the voltage, this one, or you can say the voltage is lagging the current by angle phi. Now let us see in this also, if we take V as equal to Vm sine omega t as the reference phasor here. So because the current will lead this voltage V by angle phi, so that means it will start from 5 degrees before the voltage has started. Means the current will remain 5 radians or 5 degrees ahead of the voltage. You can see at every point of time, negative peak versus negative peak. So this will always be 5. So now, because in this triangle, voltage triangle, we are calling it as voltage triangle. This V is basically a complex quantity which is given by VR, and then we have plus J VC. The magnitude here will be equal to under root VR square plus VC square. Now this can also be written as VR plus JVC, or it can also be written as V is equal to VR plus, or sorry, minus JVC. So when it comes to the magnitude will remain same in both the cases. So this quantity, now we have this one here, V is equal to VR square minus VC square, and then we have this one with us. So we have I is equal to V by this quantity here. Now you can compare it with V by Z. So when you compare it with V by Z, because Z is the resistive force, so we have this quantity which is assumed to be the impedance of the circuit. And similarly, it is denoted by Z and measured in ohms. Now let us come to the concept of impedance. What is impedance basically? Now when we discuss the DC circuits, so the DC circuits are generally composed of the resistive components. So there is no concept of the impedance in DC circuits generally. However, when it comes to AC circuits, so AC circuits will have resistance as well as inductor, or it may have capacitor also. But we have seen and we have observed that uh, the inductor and capacitor will also possess certain opposition, and it is offered to the current flowing in the circuit. Now these oppositions are known as the capacitive reactance and inductive reactance. It is the virtual opposition basically offered to the current. So that means it is not only the resistance present in this circuit which is opposing the flow of current, it is also the effect caused by the inductor and capacitor, and this is experienced in terms of the virtual opposition offered to the current. So this is what we call as the impedance. Basically, it is the total opposition offered by the circuit to the flow of current, and this is what we call as the impedance of the circuit. Now, impedance has basically two components. If you understand this with the help of the impedance triangle as shown here, so the x-axis, this horizontal component is the real component and it is the resistance, because the resistance is the real component of the impedance. And the vertical component is basically the reactance, which is given by x. So from here, you can have z is equal to r plus jx, because this is the imaginary component, imaginary axis, and this is the real axis basically. So real part plus imaginary part. Now, when it comes to the magnitude of the impedance, so magnitude is under root r square plus x square. Now, here x is the net reactance of the circuit. Now, what do we mean by net reactance? Net reactance means that there may be possibility that your circuit will have an AC source and an inductor and a resistor, sorry, and then you have an inductor here, and this is how you have your circuit diagram, right? Or it may be possible that you have an AC source, you have a resistor, you have an inductor, then you have a capacitor. Or it may be possible that you have an AC source, you have a resistor, you have a capacitor with you. So that means there may be possibility that you have a resistance and you may have an inductor, you may have a capacitor along with resistance, and you may have both the components. So instead of taking it as XL or XC, we will take it as X. So the net reactance present in the circuit. So for series RL circuit, impedance is given by this formula, where XL is known as the inductive reactance. This is the inductive reactance, which is equal to pi FL. And similarly, series RC circuit is the given the impedance is given by Z is equal to under root R square plus XC square, where XC is known as the capacitive reactance. This is known as capacitive reactance, which is equal to 1 by 2 pi FC. So now here, that means the magnitude of the impedance depends upon R, L, or RC, and the frequency basically in case of these type of circuitries. Now let us see this impedance triangle basically. So The impedance triangle is nothing but if you have this one, that if you divide this phasor with I, this phasor with I, this phasor with I, so you will have Z, XL, and R left with you. Now this is the vertical axis, which is imaginary axis. This is the real axis, which is the x-axis, basically the horizontal axis. This is real one. Now, so you can write Z as a complex quantity, and this is what we call as the impedance triangle. For series RL circuit, the impedance triangle would be like this, and for series RC circuit, the impedance triangle will be like this here. So impedance triangle is very important in many cases, basically due to many reasons. The first reason is that we can easily calculate the impedance of the given circuit from the impedance triangle. We can also calculate the power factor. Basically, the power factor is basically the true power to the apparent power. Now this is basically the cos phi. So cos phi is basically the power factor. It is a mathematical expression. So if you see the true power, if you see the power triangle, basically, so power triangle is this one, Vi, then we have Vi cos phi, and then we have Pi sin phi, right? So this is what we call as P, this is Q, and this is S, and this is angle phi. S is the total power or apparent power, Q is the reactive power, and P is the active power. So power factor is basically the ratio of the real component to the resultant. So in case of impedance triangle, you can see the real component is R and the resultant is Z. So R by Z is known as power factor. So from here we can easily find out the power factor. We can also find out the phase angle by using the same concept. Because your Z is equal to R plus JX. So phi is basically equal to tan inverse the virtual component X divided by the real component R. So we can find out the phase angle also, and we can also check whether the current is leading or lagging the voltage. Now in this case, if you see here, the current is lagging. So here current is lagging, and here current is leading. So this is what impedance triangle is. So this was all about today's class. Thank you so much.